It's been 30, 40 years or so since physicists first started talking about building a quantum computer to solve certain problems exponentially faster than a classical computer. And clearly this is an important capability, if it were true. It just was a theoretical possibility, but because of its importance, billions of dollars was being spent to do that. We expect billions of dollars to be spent in the future, and now companies are even investing in it. And we thought a few years ago, well, wouldn't it be nice just to see if this was true for kind of the simplest algorithm we can think of? And that's basically the idea with the quantum supremacy experiment. And recently, of course, we've done that, and it's great to talk about that. The day before we released the paper, I had the unique opportunity to go to the White House and brief the government about this. And I was trying to think, well, what's the right way to summarize this in a nice way? And so what I told them is that you can think of this as promises made, promises kept. And I think that, people there liked it. We got 2 tweets, one from the White House and one from Ivanka Trump. But frankly, I was a little bit disappointed we didn't get the big tweet, but that's okay. So to get there, what I want to do is talk about the new design of our qubits that's scalable and has low 1-qubit errors that allows us to do the quantum supremacy, and then talk about how we achieved it, something like 200 seconds on a quantum computer, checked with 10,000 years with a running algorithm, okay? Computation on a huge Hilbert space, never ever been done before. And also that the fidelity, the performance of the system has been validated from our low-level errors, which is basically saying that there's no additional fundamental or practical decoherent sources messing up our quantum computer, which is really important to know at this time moving forward. We feel very optimistic about it. We have our first useful application, certified random numbers, and again, we feel this is the machine that gives us practically pushing into the beginning of the NISQ era with powerful processors. So the Sycamore processor is 54 qubits, 53 worked. The basic qubits are frequency tunable superconducting transmons. What was new is the adjustable couplers between them. First of all, these couplers have low errors because you can turn them off, which really helps you make a good algorithm. And then it's also that makes it very fast at the same time. Again, that helps you lower errors. And this was very key in getting this to work. And here's the chip that you see right here. And this chip is then put into a circuit board packaging about this big or so with microwave connectors around the outside. And then on the right, you see the dilution refrigerator with a bunch of wires and filters and readout amplifiers to get that to work properly. Those wires go up to room temperature and then go to custom electronics that you can see here so that we can have kind of a dense, scalable way to do things. The 2-qubit swap calibration, the 2-qubit adjustable coupler circuit schematic is shown here. You basically have 2 superconducting qubits connected by what would be a 3rd qubit. We're not using it really that way, but it's a 3rd qubit that's at a higher frequency, and the off-resonant interaction through that green center qubit gives you an effective negative capacitance coupling with magnitude that changes according to what the resonant frequency is in that circuit. And then with that negative capacitance that can change, we add a positive physical capacitance between the devices so that at a certain frequency, those capacitances add up to 0 and we get 0 coupling. The experiment to calibrate that is shown on the left. We take 2 qubits, we put a photon into one of the qubits, put the 2 qubits on resonance, then turn on the coupling. And then with the coupling on, that excitation will swap between the two qubits, which you can see on the lower graph by the oscillating white and blue lines. And then if we adjust the coupler at a certain point, which is defined as the off point, you can see that there's no swapping going on, and that means there's no coupling. And then we move off that, we can turn on the coupling, and we can turn the coupling on and off in nanosecond timescales. So we can fit that into our algorithm very nicely. The important thing we did is we looked and did careful calibrations of what the system is. We can turn off the interactions of the qubit and look at qubits in isolation, what their gate performance is, and that's the dotted black line on the left. It's an integrated histogram. So kind of the average error of that is about 0.15%. And then we did something hard, and that was to do this randomized benchmarking kind of calibration of all 53 qubits at the same time. And that won't necessarily work if you have a lot of crosstalk in various forms. And when the result of that is in the black line, and you can see it's basically the same shape, shifted a little bit, which basically says that the qubits operating not just isolated, but simultaneously basically have the same performance. And of course, that's very important because that's how you want to run your quantum computer, just in the same way you want to run your CMOS gates. You want to run them all at the same time to make it faster and work better before you lose coherence. We did the same thing with 2 qubits. Our isolated numbers are actually pretty good, kind of state-of-the-art. Gets a little bit worse when you do simultaneous. They're a little bit trickier. Do the same thing with readout. But the point is if you want to be looking at the performance of quantum computers, you have to be talking about simultaneous operation because that's how you want to operate that. And we've done lots of measurements to understand that. Of course, that's not the whole thing you have to do, but that's something you really want to show that it's working right. And it took a lot of effort to get that to work properly. The other thing I'd like to talk about is the gates we actually make with this adjustable coupler. It allows us to build really beautiful gates. Usually people just make a gate. Let's say you make a C0 or equivalently a CZ. We can actually make a larger family gates, both doing the CZ-C0 as well as doing I-swap gates, which are the blue elements in this unitary matrix. And this is very nice because if you want to do quantum chemistry simulations, you want to put in excitation preserving unitaries in there to do the simulation, and we can directly synthesize that with our coupler gate, making it more efficient, making it faster, making it run better. And here's an experiment done by Brooks in preparation to be published very shortly, where we made a whole array of different thetas and phis and show that we can synthesize to that. And in fact, we can synthesize that with a fairly low error and measure things like that. So we have a very good gate set, fast gate set, efficient gate set to work with this architecture. All of this requires lots of calibrations. I'm not going to go into this. It's very complicated. We have a very systematic way to do it. And I've circled 2 nodes here, which was essentially the PhD thesis of one of the workers here. So there's a lot of stuff going on here to get it to work. Okay, we spent a lot of time figuring out calibration, especially when you have frequency tunable qubits and the couplers. You have to tune that all right, but you can do it. This is all automated now. We cool down our chip, we run automation program, more or less gets everything right automatically, let's say in a day or a few days or so. Okay, just to summarize this, a lot of times people like to use a single metric for a quantum computer. I kind of don't like that because that's not what we do with your cell phones or anything else you buy. Maybe perhaps with price, but I would not use price as a really good metrics. So there's a lot of metrics in the system. The basic 3 ones given here is the number of qubits, the error, usually the worst error is 2-qubit, and also 2-qubit error, as well as the connectivity in the architecture. So what we see here is in the UCSB data, which is what we took before coming to Google. We had made a 1D array had nearest neighbors connectivity of 2. And in the Sycamore chip, we went to a 2D array with nearest neighbor connectivity of 4, which is surface code compatible. So everything we're doing is forward compatible for long-term getting to error correction, which is we want to do. To make an error correction, we have to get below the error threshold here, and we probably want to get around the 10 to minus 3 error and then scale up to million qubits. So the nice thing about this experiment, although it's taken us 5-6 years or so, we increased the number of qubits, we decreased the error, we made the architecture more complicated, all in one device. So we're making better. And I would like to say this open circle is kind of the best 2-qubit gates we get. So that's something where we think the limit is. And, we think with a little bit more, we can get down here and get on this curve and then, seriously start thinking to build a quantum computer. So this is fine for doing our initial experiments. We still have a ways to go and then know how to scale up. Last thing I like to say is these are individual single 2-qubit errors. How do we know those errors are valid and appropriate for building a real system? We need some kind of system validation to show that. And that, in fact, what the quantum supremacy experiment is, one sense, all about, is showing that the system validation really works properly. So here's the control sequence for the quantum supremacy experiment. And what we're doing is interleaving single qubit gates, which are the individual circles, with 2-qubit gates, which have a line in between them. And because there are 4 nearest neighbors, those lines rotate around the 4 nearest neighbors. And all of these things are done simultaneously. And also, like I'd point out, that this is basically a general purpose algorithm where you're interleaving single and 2-qubit gates. So it's a nice experiment in itself, but it really tests what you want to look at for a general algorithm. For the particular center qubit here, you can see how it's connecting with 2-qubit gates to the neighbors. And then what we do in the quantum supremacy algorithm is we have a fixed 2-qubit gate, but we have randomly chosen but known single qubit gates, which are pi/2 rotations, either around the x-axis, y-axis, or an axis in between. And that produces a final state here. Single qubit gates are about 25 nanoseconds. 2-qubit gates are about 12 nanoseconds. So these are all fast, and we can do a lot of operations before we lose coherence. With coherence times T1 is about 15, 20 microseconds. So we do that algorithm. It checks a general purpose circuits, randomly chosen gates. You would expect naively there's no structure in here to have the output probability kind of uniform of all the states, but what happens is what we call qubit speckle, which is similar to laser speckle, where some of the states are higher probability and some are the lower probability. And the only way to know which are the higher and lower, there's no real structure in here, it's very chaotic, is to do a simulation. So we have the quantum supremacy experiment, we run it through the chip and get output bit streams. We then also run it through a classical computer and get probabilities for all of the 2 to the n states. And then we combine them in a cross entropy where for the measured values, we put in these probabilities. And since the measured ones are higher probabilities, this probability here will be greater, it's a little bit greater than 1/2 to the n, and the fidelity will be 1 if there's a perfect match, no errors, or if you make a mistake anywhere, you get 0 for error, okay? 0 error. So this is great for system map validation. You can learn the control map, extremely useful in bringing up the device. So here's the data. Here's this cross-entropy fidelity. We start at 12 qubits with 14 cycles, and that's about per qubit. That's about, 28, 29 operations per qubits. That's about 250 gates for this data point right here for cross-entropy, about 40% fidelity. And then, of course, as you increase the number of qubits, there's more chance of error. If there's a single error, the fidelity goes down to 0, so the fidelity goes down. But we can see a statistically significant non-zero fidelity down here up to about 53 qubits. And in this particular case, we can test, do all the classical simulations and get the fidelity. And you see it follows a nice line here, and we can do that. We can also, instead of the full circuit, we can cut the circuit in two, which is a lot easier to simulate. Those are the blue crosses, which fall on top of the data here. And we can also do something in between where there's not a full cut, but it makes it similar to simulate. And again, all this data falls on top of each other. So this is all verifiable. We can run that. Of course, what we can do is go into the supremacy regime. It turns out there's a mathematical trick that makes this easier, and you can just change the sequence a little bit so that mathematical trick doesn't work. And now the time it takes to simulate this gets very large, and we don't have the red circles anymore. But we can simplify the circuits in this way. We expect it to fall on the same line given here, and we have non-zero fidelities, and thus you claim quantum supremacy. So that's the basic idea here in doing that. Now I want to make really one important here that totally amazed me when I started seeing this data. And it's the fact that if you look at the full circuit here and the simplified circuits, they all lie in the same line. And in fact, the prediction from just the gate errors, 1 and 2 qubit 8 errors, you figure out what all the probabilities are from all that, simple calculation, they all lie on a straight line. They're all together. This is truly amazing. And I'll talk about the implications from that. Okay, why does all this data lie on the straight line? That things are working really well. Same fidelity, full elided patch, even predicted. The errors are not dependent on entanglement and computational complexity. That's surprising, okay? Or, at least for an experimentalist, you expect things to go wrong, right? This is great. This is what you expect, theoretically. But in an experiment, that's wonderful to see. The fact that the predicted gives you the fidelity says there's no new decoherence physics beyond what we've been measuring in single and 2 qubits. And a simple formula predicts the fidelity. This, again, is what you expect. This kind of says that error correcting should work at a very deep level. Okay? We're doing computations on 53 qubits with about a 10 to the 16 Hilbert space. This has previously been tested at about 8 or 10 qubits at about 1,000 space. So we changed the computational complexity, whatever here, by 10 to the 13, and nothing new happened. That doesn't happen very often in physics, but it's cool that it did. We expected it to did, but it worked. Fourthly, this is great because we can test the model of digitized errors. This is data for the cross-entropy benchmarking in red dots. This is where we operate. But at one of the gates, out of the 500 gates or so, we put in a phase shift between 0 and 2 pi. A pi is a phase flip. And you see the fidelity goes down to 0 and then comes back up. And this is what you expect out of the algorithm. A single phase flip, single bit flip destroys the fidelity. And in fact, it follows the cosine squared dependence very well, as you expected from theory. One error gives 0 fidelity. It's consistent with error probability and the assumptions of error corrections. And what's really cool here is you can test the performance of each gate in this sequence. You can test the performance of 500 gates in this by looking at this. And you see the red dots are shifted over to the right a little bit from the prediction, which says that that particular gate was a little bit different. Let's say you can even say miscalibrated, although it's more complicated than that, than what we expected. And that's really good information for learning for what's going on in your system. So this is very important. Okay, let's talk about the first application, a certified random number generator. I'm 100% sure that we can get this to work. It's essentially an experiment we did. But of course, will people in business thinks it's important? Okay, that's another story. But let's try and figure that out. What's the problem with conventional random number generators? You have a physical mechanism of a random number, and then that number somehow gets into the computer. And you wonder, well, is there some hidden correlation in that number, either intrinsic or put in, say, by a hacker who's done something with the hardware that they can exploit and not have a real random number. And what's nice is the certified part of this says you can show that the quantum random number has a provable origin, so you know it has the proper random. So what you do is you just generate these bit streams of random numbers, and you can distill them and figure that out. But you can also use the correlation that's in there from the known circuit that you put in to verify that the random numbers were created with a quantum algorithm in the way that I did the experiment. And then you also timestamp from here going to here. Let's say it took a second to get those random numbers, and you know that verifying them on a classical computer would take minutes or hours or days or some huge number, and then you can prove that the random numbers created with hardware. And the combination of these two things is the certification that came from a quantum circuit, and you can trust the random properties of that, which are provable from quantum mechanics. So that looks pretty interesting for people who really want to be careful about their random numbers, and companies like Google and other places really care about that. Okay. When I give talks, I'm always asked about the IBM press release. So let me talk a little bit about that. First of all, I want to publicly thank IBM for their press release, because the controversy, whenever that's generated, generates a lot of press. And we got a lot of press for our paper, and that was great. I wanted people to know about it and hopefully read the paper. And I think one of the, amazing, amusing things is some kind of discussion of that, scientific discussion of what was going on here, occurred with Scott Aronson in the New York Times editorial. So how special is that? That's really great. Now, what I want to do is talk a little bit about an experimentalist view of what's going on here, because I think there's something to learn here. First of all, I wanted to say that there are a lot of comments about this, but it's like no one read the paper. Okay, if you read the paper, okay, here's the paper. We expect that lower simulation costs than reported here will eventually be achieved. So, we expect it. And the reason we expected it is if you go back to our data between validation and supremacy data, it just happened there. We figured out some clever trick, mathematical trick, and it happened to us, and we had to take more data. So, okay, no surprise there. But then we said we also expect that they will be consistently outpaced by hardware improvements on larger quantum processors. So, fine. This is something we expected. So it's a nice algorithm where they use disk memory to increase the capabilities of the Summit quantum computer. However, I want to remind everyone that this was a proposal. They actually have not actually run the algorithm. And I don't know if you know the computer science field, and certainly this is an experimental paper. You have to actually do it to say if it's true. And particularly in the case where if you're going to use hard disk memory as part of your algorithm, that's not how superconducting computers work. So I expect it'll work, but it's not trivial at all that it's going to work. And it's tricky to write supercomputer codes and failures and whatever. And one of the interesting things I've learned since then is that when you use disk memory, that actually uses a lot more power consumption. And that's not originally how the Summit supercomputer was made. But fortunately, they can start trying this now because they have some more power coming into Summit from a nearby nuclear power plant. So let's go for it, okay? Go for it now. Now, I can absolutely guarantee we can add 2 to 4 qubits to the Sycamore so that this program can't run anymore. So, okay. We did not collapse over the finish line. But I think it's great. There's going to be this race in the next year between, adding 2 or 4 qubits versus a nuclear-powered algorithm. And what's great, this is what I love, is whoever gets there first, we can still claim victory for quantum computation. So we have 2 ways to win. It's great. This has all been fun. Mostly, that's why I said it. But I do want to say all of this, it's great. We have to do it. It's good physics. Let's do it. It's really kind of a distraction from the real issue. What's the real issue here? This is the reason I'm bringing this up. What's the real issue? The real issue is, what is the performance of the quantum hardware? Okay, and that's what we were able to do in this thing. Okay, so I have 3 minutes left. That's perfect. Let's talk about business applications. That's a business audience here. One of the funny things is people are talking about putting out quantum computers, and when I read these marketing releases, it kind of treats quantum computers as a commodity, kind of almost like what cell phones are. Okay, that's reasonable. Quantum computers are not a commodity. The reason we want to use them is because of their exponential power. With qubits, with performance, with resources. If it's exponentially more performant because you did a little bit better, it's more of a winner-take-all situation than a commodity. I understand it could be complicated. All I want to say is the drive in my group, in what I'm doing, and what Google is doing, is make the best system performance possible. And that's why we haven't really done a cloud offering yet, because we've been working on making a powerful computer. So we have one now. We're going to get it out there. I think people are really going to like it, because the performance is good. And we need to understand that better, but it's going to be there for you, okay? The other thing I'd like to say is to get this experiment to work required a lot of breakthroughs and understandings in systems engineering, getting more qubits and lower errors at the same time. This is really hard. I'm sure people in the Air Force understands that, for example. And we have a lot more to go, but we think we've gotten over some of the hardest things here, so you can expect better performance devices. In fact, as of last June, we had some better performance devices, and we'll be talking about that. So things are working well. It's going to be even bigger and better. Okay, we have to work through that carefully. The final thing I want to say in terms of the customers and programmers is, people, please, of course, people are probably doing this, thinking about how you can use these new processors that are quantum supremacy capable. And it's a really exciting time. I want you to just think about the situation now. You might be able to develop algorithms that you can't run on a classical computer. I mean, it's possible now. I'd like to say it's one idea away from compelling applications, either on the chips we have now or the chips we're going to have in the next few years. Please be thinking about that, because that's what we need in the field, as has been talked about, say, by John previously. And when you start thinking about that, you think you have an idea, please come talk to us. We're really interested if you have a quantum supremacy kind of algorithm that can't be classical simulated. You work with us, we can try to get you in as soon as possible to test it, because my feeling is if we can really get these kind of user applications and really make a big difference and do something that you can't do in any other way, that's going to radically change our field and make us all the more successful. So please journey with that in mind with us. At that, thank you very much.
Hi. I noticed on your graph, readout errors were much larger than the 2-qubit thing. Could you talk a little bit about that and what?
Yeah, I'd love to.
Okay.
What happened is this was the first device we cooled down. We designed our readout and we didn't hit the parameters right. So they were close enough to get some readout, but those errors were really too high. Now since then, we've developed good physical, and of course you could always iterate the chip to make those parameters better, but we didn't do that. Instead, we figured out, why those parameters were wrong, and we have better physical models. And the second chip, which we made June or July or so, we hit those parameters, and the latest numbers are, significantly better, kind of within the normal range that you would see with this. So that's one of the things that we fixed. And again, we're going to continue to work on that. But yeah, that was the first chip we cooled down from just the design, no iteration of parameters, and we got the experiment to work. So, little things did go wrong. Easy to fix, though, in that case.